am not a chemist, okay? I took chemistry 3 times, once in high school, twice in college, and earned a D all 3 times. So it was not until I'd been a potter for about 5 years and finally established my own studio that I suddenly said, oops, how do you make glazes? So I had to sit down with the books and learn what little I do know about chemistry. Our cosmos is composed of mostly empty space. There's energy, there's force, and there's matter. And as Cerealists, we're concerned with all 4. Of course, we can't create space on the planet because nature will not permit a vacuum. But we do consider space when we're loading kilns. The ones we have in the back, the more tightly you stack them, the more pots you can squeeze into them, the more efficiently they fire. But if you're using a fuel-fired kiln, you have to leave space between the pots called a flame path. And let me clear up a misconception many of you may have. Pots are not fired by flame. They're fired by air. As the air comes into the firebox, it becomes superheated either by the coal bed or the gas jets. And as it passes through the kiln, it disseminates that heat to the pots. Flame will make marks on pots, but it does not fire them. We constantly battle force. It's our great nemesis. Centrifugal force wants the clay to go this way. We want it to go this way. And of course, there's our good old enemy, gravity, that always wants it to go this way. Matter, that's what we're concerned with today. Matter is anything that you can see, touch, taste, or smell. It exists in 3 phases: gas, liquid, and solid. Now, we can't create cold. All we can do is take away heat. There's no such thing as cold energy. Steam has absorbed enough heat to become a gas. As you deny it heat, it undergoes what is called a phase change to water. As water is denied heat, it undergoes another phase change to solid ice. Okay? Now, the basic building block of matter is the atom, and it is composed of a nucleus, which contains protons carrying a positive electrical charge and neutrons which have no charge. Then there are the electron shells, which contain electrons, and they are negatively charged. The electrons swirl around the nucleus, and they are held in place by the electromagnetic attraction of positive and negative charges. Now, don't think of an atom as a little solar system. The planets orbit the sun in predictable orbits. That's how we can know where Jupiter is going to be on this date 10 years from now. The electrons move erratically. They don't have any particular pattern in terms of their rotation around the nucleus. The first electron shell is called the K shell. Now, I've often wondered and never found an answer. Since it's the first one, why isn't it the A shell? or the first shell. It's the K shell. It has room for 2 electrons. All the others have room for 8 electrons. Glasses, that's what I can't read. All atoms strive to have a closed outer shell or complete outer shell. Now, we have hydrogen, which has 1 proton, 1 neutron, and 1 electron. The K shell has room for 2. So hydrogen has an incomplete outer shell. Helium has 2 of each particle, and so it has a complete outer shell. This means that it's chemically inert. It can't react with any other element. It's a member of a group of elements called the noble gases or the inert gases. All atoms which have the same number of particles are members of a family called an element. All helium atoms have 2 protons, 2 neutrons, and 2 electrons. And any atom that has 2, 2, and 2 is helium. So, now, from time to time, atoms of one element will combine with atoms of another. And when 2 or more atoms combine with each other, you have a molecule. Now, oxygen has 16 of each particle. So in its K shell, it has 2 electrons, L shell 8, M shell 6. So its M shell has room for 2 electrons. So what does oxygen do? It goes out and it finds 2 hydrogens and inserts their electrons into its M shell. So now the oxygen and the hydrogen are sharing electrons. And the electromagnetic attraction that holds the molecules together is called a valence. Some valences are fairly strong, others are rather weak, which I'll demonstrate in a moment. You know what that is? That's clay. 1 aluminum oxide, 2 silicon dioxides, and 2 waters. When you impart enough heat to matter, it begins to vibrate at the molecular level. You can't see this, it's too small. But it does happen. And when clay absorbs enough heat, The vibration is so strong that the valence between the water and the other three molecules is not, won't hold it in place any longer. It gets thrown off into the atmosphere, just like steam boiling off a cauldron. When that happens, the aluminum and the silicon reconfigure the electrons in their outer shells to form a complete outer shell. This means that the material is chemically inert. You can smash it, you can grind it to cake flour, but you'll never change it at the molecular level again. And this is one of the things that makes it so important to us, in that when ancient pottery is uncovered, we're able to determine whether it was earthenware, stoneware, porcelain, and roughly the temperature at which it was fired, which means that we can determine the ability of the civilization that created it to control fire. And that's a relative measure of their level of technological sophistication. Okay. It's important that you understand this concept because you're going to use it today. We live in a very technological society, but even our advanced technology is not sophisticated enough to isolate and actually weigh an atom. They're too small. If you had a grain of sand in your eye composed of 1,000,000 atoms, you wouldn't feel it. They're that small. But we have to have a way to differentiate them, and this is especially important in glaze chemistry. Atomic weight is a relative deal. It's how heavy is this atom compared to this atom. And we know that hydrogen, with only one of each particle, is the lightest atom, and so it is assigned an atomic weight of 1. Helium, with 2 of each particle, is assigned the atomic weight of 2. Lithium, can you get the periodic table? Is number 3, because it has 3 of each particle. So it's 3 times as heavy as hydrogen. And you see here on the periodic table, top left is helium, or hydrogen, top right is helium, just below hydrogen is lithium, so they're 1, 2, and 3. Now you'll notice the atomic weight is always equal to the number of particles that the atom has. Now, we have molecular weight. Molecular weight is simply the sum of all the atomic weights in a molecule. Let's not do that. Silicon dioxide, something we use every day in glaze chemistry. Silicon has an atomic weight of 28. Oxygen has an atomic weight of 16, but there are two of them, 28 and 32, sum to 60. So the molecular weight of sodium dioxide is 60.
Right, okay.
Where are we? All right, now, in Glaze chemistry, we have to use the metric system. English system is too bulky and cumbersome to get the job done. I mean, what is it with 12 inches in a foot, 3 feet in a yard, 16 feet in a rod, 5,280 feet in a mile? It's not a system, it's a random number table. But the metric system makes sense because it's predicated on our planet. Scientists determined the diameter of the Earth at the equator, divided that distance into 1,000,000 pieces. Each of those pieces is a meter. A meter is divided into 100 pieces called centimeters. So if there are 100 centimeters in a meter, how many centimeters in 7 meters? 700. Now, without pencil and paper, how many inches in 7 yards? You can see the superiority. Now, we don't use linear measure, and we very seldom use volume measure, but we do use weight. And the basic unit of weight in the metric system is the gram. A gram is the weight of 1 cubic centimeter of water at standard temperature and pressure. This means 32 degrees Fahrenheit at sea level. Okay? Now, the reason we do this is because in making a glaze, you have to achieve molecular the reason I write so poorly so you won't see my misspellings. Molecular equivalency is best demonstrated than explained. If you have a glaze formula which calls for 1 part lead oxide and 1 part silicon dioxide, you can't just weigh out a kilogram of each one and stir it up, because lead is much heavier than silicon. Consequently, you have way too much silicon and not nearly enough lead. So what do? You find the molecular weight of lead oxide, 223, and the molecular weight of silicon dioxide, which we've already seen, is 60. So you weigh out 223 grams of lead oxide and 60 grams of silicon dioxide, and you will have a 1-to-1 ratio of molecules. And that's what we call molecular equivalency. And as long as you maintain the proper ratio in your dry mix, it doesn't matter if you're weighing grams or metric tons, you're going to have the same molecular equivalency. This is how we think about the materials in a glaze form. R stands for radical, and that just simply means any chemical substance. In the RO column, we have the fluxes. Now, you see in a periodic table, on the left, you have lithium, sodium, and potassium. These are the alkalis. Just to the right, magnesium, calcium, strontium, and barium. These are the alkaline earths. So we talk a lot of times about alkaline glazes. These are glazes that use some combination of these elements in the RO column, the fluxes. Flux is simply something that causes the silicon to experience a phase change. And the type and amount of flux determines the temperature at which that occurs. In the R203 column, we have the stabilizers, aluminum oxide and boric oxide. These are the components that keep the glaze from streaming down the side of the pot onto the kill shelf. And in the RO2 column, we have the glass former, which is always, no it's not, which is for the most part silicon dioxide. But these things get a little fuzzy because calcium borate or colemanite or Laguna borate, there are a lot of names. Actually, the colemanite was mined out years ago, but it was simply calcium borate, and so it can be artificially produced. So in this case, we have a flux and a stabilizer going into the glaze. And there are certain occasions when boron can become the glass former. So it's kind of an incestuous group. We also have other glaze components. such as deflacates. Most common is bentonite. Bentonite is a clay that is derived from pumice, volcanic ash. And it is an electrolyte. Each molecule has a positive and negative pole. And as you know, like charges repel one another. By stirring this into your glaze, since most glaze components are fairly dense materials, they tend to settle very rapidly. And if you don't keep them in suspension, then you don't get the proper coating on your pot. You just get a bunch of dirty water. But bentonite will cause the particles to stay in suspension. Casting slip is eat up with bentonite. Because otherwise, you'd get a heavy concentration of material at the top of the cast and a low concentration at the bottom when it was empty. Now, there are some glazes, especially those that are fluxed with lithium, that have a tendency to settle in the bottom of the bucket. And I mean settle. If you dump the water out and take some kind of tool and dig into the glaze, you'll find it dry in the middle. If you have that problem, stir about 2 cups of Epsom salt into the bucket. Epsom salt is magnesium sulfate, therefore it doesn't fit into any of the R columns, has no effect on the glaze whatsoever, but it is an electrolyte and will keep that glaze from settling so hard in the bottom.
Is that in like a 5-gallon batch that you would add 2 cups?
10,000 grams. There are opacifiers. Now, everything I talked about in the R columns makes clear glass, just like the windows. So if you want to be able to see through the glaze to the pot, where you've perhaps done some sgraffito or underglaze decorations, then you don't want to put any opacifier into the bucket. But if you want the glaze to be if you don't want to see the pot underneath the glaze, you add the opacifiers. The most common of these are tin oxide, all of these are artificial. Tin works the best, but it's also the most expensive. So if you're on a tight budget, you want to go with one of these. You're going to talk about colors, right?
Yeah.
Something else we add is coloring oxides, which Megan will cover in her part of the program. Now, we come to cones. For thousands of years, there was 2 ways to determine if your glaze had experienced a phase change. The first was to have some codger like me sitting around on a bucket who could look into the firebox or the wear chamber and say, okay, it's been the right color for the right amount of time. And then there were draw trials, which are little rings of clay that were bisque fired and then half dunked in the glaze. These were hung on iron pegs inside the firebox, the wear chamber, and at certain intervals they would be pulled out with a poker, quenched, and then examined to see what condition the glaze was in. This was all prior to the advent of modern chemistry. But in 1884, a man named Otto Sager was running a production pottery in some place in Germany, I don't know where. And he reasoned that if he would cast his glaze in a mold, in this shape, then he could stick this in a pad of clay, put it in front of the spy hole, and when it melted, he would know that the glaze on his pots had experienced their phase change. I've provided you with a table. It's a cone chart. Tells you the relative temperature of each cone from 022, which is approximately armpit temperature, up to cone 15, which is the temperature at which the tiles on the space shuttle were fired. Why are there so damn many? You would think. You know. Oh, and as for the O's, these temperatures are predicated on the melting points of fluxes. They have nothing to do with rhyme or reason. And the reason we have the O's is because the temperature Sager was trying to reach is what we refer to as cone 4, the very bottom of the stoneware spectrum. There's no need to applaud, simply throw money. That's everything I can tell you. Anybody have a question about anything I said?
Our minds are blown. I don't know what to think.
Oh, one other thing. I provided you a page out of Jim Chappelle's book, Potter's Complete Book of Plain Glazes. It's in the back in the bookcase. You're welcome to have a look at it anytime. It has a lot of valuable information in it. But this is just to give you an idea of what you're looking at in terms of adding or compiling a glaze from scratch. And this, ladies and gentlemen, is the Holy Writ. Clay and Glazes for the Potter by Daniel Rhodes. Rhodes was the most influential potter of his generation. He was professor at Alfred College of Ceramics, State University of New York. He wrote multiple books, but this is his most famous. For technical material, it's extremely readable. I've read it 4 times myself and referred to it countless times. It's out of print, has been for decades, but you can find a copy on eBay. You pay through the nose for it, but it's worth every brass farthing.
That's where I got mine.
Daniel
10 years
Rhodes,
ago.
right?
Right.
Paperback.
same information.
Right, yeah.
Alright, so we're gonna move to the hands-on portion. And so just to review about glaze chemistry, so we're gonna be talking about 4 different components, actually 5 if you count pacifiers. So all glazes have a stabilizer. The stabilizer that we're gonna be using is gonna be Edgar Plastic Kaolin. That's just a name for it. Edgar Plastic, a brand name. It's Kaolin. This is so it doesn't run off your pot, the stabilizer. The glass former is silica, of course, flint, quartz. You'll see a lot of different names for it in the recipes. Flint if it's like a European or English recipe. And then Frit 3134 is gonna be our flux. This is a commercial made flux because it is a frit, which means that it's not mined like a lot of those other elements are mined. And so 3134 is a boron based flux. And so I'll show you the difference between that and how it looks. And then we'll be adding colorants as well as opacifiers if you don't want a translucent glaze. So stabilizer, flux, glass former are the base glazes. And then you add the colorants and opacifiers. So those are the additions. Okay, and last one over this. So silica, that's like a nickname for silicon dioxide. We have our stabilizers. You have the kaolin, bog clay, bentonite. Those are all different names for the stabilizers that we have back in the chemistry lab. But we are using kaolin, China clay. Periodic table, these are all the different fluxes. We're going to be focusing on frits. So frit is a really, there's, how many frits are there? Like hundreds?
Oh, God.
So many different frits because they are chemically made so that they are a low fire flux, where like lithium, calcium carbonate, all those other ones are high fire, so mostly used in cone 10. But you can use frits or get like earthly boron to bring down the temperature, also lithium. And so colorants, we're going to be discussing heavy metals. These are all the colorants on this table here. So iron, that's going to give you those yellows and browns. We have 2 different types of iron. We have red iron oxide, and then we have Spanish iron oxide. Did you bring out black iron? We don't have black iron. Oh, we do? So we have black iron somewhere.
No, it's copper.
Ah, here it is, black iron oxide. So
She
those
said the
are,
black irons give you what colors?
it's all going to be like the brown, the yellow irons. And this is iron oxide and 3134. So frit by itself is just glass. You can take frit, I put frit in here, I heat it up to cone 5 and put some of the iron in it. Now we are adding the stabilizer so it doesn't run off the pot. If I were to put this right on the pot, it would run off. And the glass former, because if you look close, it's crazing. So it needs that glass former to fill in those cracks so it's a solid, stable piece of glass. So that's iron in the flux that we're using. Chromium. So this is going to give you greens. If you mix it, let's see, with some tin, you'll get pinks as well. It can give you browns. That's a bright green. And you can see in this boron-based flux how it has this opalescent look around the outside. So that's different than some of the other frits that are more clear. Going on to copper, so you'll get blues, greens. Now, if we're talking about oxidation, and that means that we're not reducing it, so with like gas where you're reducing the oxygen, if you were to reduce it with copper, you're going to get your reds and pinks. It's very, very hard to get reds and pinks in oxidation. That's why they make mason stains, which I'll show you what this looks like too. So cobalt, you're gonna get what color?
Blue.
Blues, good job. You can also mix it with manganese, red irons to get more of a purple shade. And so the cobalt we have is cobalt carbonate. There's also oxides, and oxides are heavier, so you would have to use twice as much cobalt carb if your recipe causes for an oxide. And the same, there's copper oxide, copper carb, manganese as well. And I can send you this PowerPoint since I'm going to
Oh, good.
So rutil, this is how we're going to get titanium. It also has some iron in it as well. And the rutil is right here. So it's this brown color. The reason that you would use Rutile is if you want some depth in your glaze, so it's going to cause like streaking or speckles. If you've heard of blue Rutile, how it makes that like opalescent look, that's due to the Rutile that's in it. So it'll also by itself, it'll give you like yellows, browns, or a little light in a color. And manganese. So this is very hazardous to breathe in. Just be careful any of these materials really when you're breathing in. But this is going to give you browns. It can also give you purples and pinks. And let's see if I do have manganese. So when you look at it, like in the middle it's brown, but then it's purple on the outside. So I'll paste that one in. This is the cobalt, again with our boron-based frit. And this is Rutile by itself, so you can see that milky look. So that's that from the Rutile blend. And we also have nickel. Now, nickel can dull a color. We have nickel oxide, we have nickel card. And then, what is another one? Burnt umber, that's going to be more of that iron based as well. There's ilmenite, which you'll get titanium and iron too. And so this is an example of a triaxle blend where it has iron, rutile, copper, chrome, cobalt, manganese. I also have the real thing over there if you want to look at it and how they do it, where they meet and the color combinations. Now this is on a sodium-based frit, so it's a little more clear. And then we have opacifiers. So you get to choose from all those colorants, and then if you would rather have an opacifier, because the Izzy's glaze that we're using, it's called Izzy's because I got the recipe from Israel Davis, who prints on clay, and he's a phenomenal artist, so look him up. But that is our base glaze, so the Izzy's clear. It's a translucent clear that uses the frit as the flux. If you want an opacifier, so if you want to not be able to see the clay underneath, or the opacifier does not melt at that temperature, so it's kind of suspended. So when the light reflects it, it's going to give you a different color. So if you want a yellower kind of color, you're going to choose Zircopax. Zircopax gives you a yellower white, where zirconium or tin oxide is going to give you those bluer whites. Also, white tin oxide is more expensive, and then Zircopax is not as expensive as zircon. So if you want more opaque glaze, you're going to want to add those into your formula. Then there are frits, colored frits. These are also by brand name Mason Stains. And so the way that these are made is that the chemist melts the glaze up to a certain temperature. They take that glass, they grind it back down into powder. So then when you put it into your glazes, you know exactly what you're going to get. And these are pretty expensive. I don't think we have any of these to experiment with either. But we're learning the real chemistry, so the colorants. So at your area, you should have a sheet like this. And so you have your clear base glaze, so 100%. We are going to be mixing 1,000 gram batch of that clear base glaze. So 3 components. We have to have the glass former, silica. We have to have the flux to melt it at our temperature that we need, that frit. And then the kaolin so it doesn't run off the pot, the stabilizer. And so I'll demonstrate how to mix that. And then the bottom part is when you're going to start to add in your colorants. And so we'll do this step by step together. The first thing that we're going to do is mix that base glaze. And then after everybody does that, I'll show you how to mix the colorants into it. And if you want to do a line blend and whatnot. Any questions about that? I'm going to switch to my N95. So what can happen to pliers is they can get silicosis. We don't want that. Alright, so I'm going to grab you all have a yogurt container. And so before I go over there, I have to tear it out. Do you say tear or tar? We were discussing this earlier.
I learned it as tear, but
Tear, okay.
I studied everything up north, and I've noticed that there are some words you say different than what I say.
Oh, really?
Yeah.
I say tear just, or
Like
tar,
rutile?
just cause that's what.
Oh,
that's what it
yeah,
smells.
retail.
Yeah, no, like I've always,
Rutile.
but there's
Yeah,
there's
there's
there's a
different ways.
handful that
So
you
I heard
said
it
that
different
I'm
ways
like,
too. That's why I was like, what do y'all say?
yeah, no.
Alright, so you tear it out. So you put it on there so it goes to 0. Now the first ingredient I'm gonna grab is, I'm just gonna go ahead and grab the frit since it's over here. So I need 500 grams, so it's 50% of that flux material so that it melts. It's also really important that if you don't get, or if you get too much, that it goes back in the so it's leveled up there. So 500 grams is gonna be pretty much close to the top. And then we're gonna be putting this into our Ziploc bag, so that's 600. So I'm gonna take some out. I'm just gonna grab my cup. So has anybody mixed glazes before?
We did these with you once. I made Izzy's with Les a really long time ago.
Oh yeah.
But you made it.
This is like the easiest, best glaze to learn on. And so you all have a digital scale. The reason that we have the balances out is when you get to the colorants and you're measuring a fraction of a gram, the digital scales don't work as well. $99.8, 500. Ah, okay. And it's really important, it's precise, since we normally mix in like 2,000 gram batches, and then you'll be going to 100 grams. So you want to make sure it's completely precise. Now I'm going to take this one back to the frit. If you forget where you got it, just throw it away.
One person can screw it all up.
Yeah, we don't want it to go into the silicone. Alright, so now I'm going to take that. I'm also going to make a mark so I know. Alright, I got 500 grams of frit.
Always, always, always write down what you just did.
Oh,
Because the phone will ring, somebody will knock on the door, and you come back and you say,
What
did I put 2,000 of that or 3,000?
Yeah.
And the only solution is to pour everything in the bucket down the drain and start again.
Yep. So
It's
now
like ripping up money.
Yep.
silica coarse flint. The reason it's called flint is in England, that's how they would get their source of silica from the flint rock that would wash up on shore. Now I gotta need 200, so.
It's like we're watching the British Bake Off. They do everything in grams and, you know, their flour.
You know, they do have the throwdown, fiery throwdown. We could do a glaze throwdown. Alright, so 200. So this is denser by particle size. So 200 of that. Any questions while I'm doing this? Should I quiz you? What is in a base glaze? What are the 3 components?
Silica, frit, and Taylor.
Well, it could be, yeah. So then, what are those, like, the glass former, the stabilizer, and the
The flux.
and those crystalline glazes hardly have any, the ones I have up front in the white plates, hardly have any stabilizer because they have to run, which is why they're in plates. All right, 200 grams of silica. And now we're moving to 300 grams of kaolin. And there's different brands, like, and there's Brolic, which is going to be a wider kaolin, so you would use more in porcelain. like a bentonite. So that's $2.97. So this is a lighter material. Oh wait, I said 300. Almost there. Now once I get into the Ziploc bag, I'm gonna spend about 5 minutes massaging it, shaking it around, and then you all are gonna be doing this part. And then we'll go over the mixing the 100-gram batches. So what colors are you all thinking? That's the hardest part. I spent like probably 10 minutes coming up with my little formula I was gonna do. I can pull back up the colorants too. Or you're welcome to look over there at that grid. Alright, so now I'm gonna sit here and massage this and shake it all up while you all start to mix. Cool, so turn on your scale, make sure it's working right. You want to tear out your yogurt container.
So I'll put it on there.
And remember what you come and get.
So then it's a
And I had that unplugged, Susie, or you're getting it.
I plugged it in.
Okay. So Les, I only need 200 grams of this if you want to play around with some of it. Yeah. Because I'm going to do 2 lime blends.
Even if I do this, we're not gonna have enough tiles for 10.
We made extra though. See how many are back there.
Good.
18.
So, well, you can do 8 of them. No, you have some on your glaze table.
Oh, I do, don't I?
Yeah.
Okay.
Make sure your Ziploc bag is sealed really well.